Oh yeah, let's write lines as equations. That sounds like fun. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are taking a look at our first family of functions, linear functions. Linear functions are any of the family of functions that have a constant rate of change. The parent function looks like this, just a diagonal line that passes through the origin, where each increment of x equals one increment of y. But that's not very interesting. Let's add some flavor to this function. Y is equal to ax plus b. This is called the standard form of these functions. Now you'll often see linear functions written in this way. Y is equal to mx plus b. M and a, in my notation, do the same exact thing. They represent the slope of the function. Now I'm electing to use the letter a for my leading coefficient here for exactly that reason. In higher order polynomials and other more complicated functions, the leading coefficient is often represented by a. So here, instead of using my leading coefficient as m, I'm going to use a, just to connect it with higher order polynomials and other sorts of functions. But in general, a is equivalent to the m you'll probably see in class. The nice thing about this form is that it gives me two properties of this function right off the bat. A is equal to the slope of the function, and b is equal to the y-intercept of the function. But linear functions can also be written in something called point-slope form. I'm going to write it like this. Y is equal to a times x minus h plus k. You'll also see point-slope form written in this form. Y minus y1 is equal to m times x minus x1. Again, I'm using h and k and a in order to reflect what we'll see later in more complicated functions than using the more traditional y1 and x1 notation. But again, these functions are entirely equivalent. And in fact, point-slope form is entirely equivalent to slope-intercept form. They're just different ways of writing the same functions, and these different ways have different utility in problem solving. We already talked about the utility of slope-intercept form, but point-slope form also has its own utility. For instance, h is equivalent to the horizontal shift of the function, and k is equivalent to the vertical shift of the function. In both forms, a is equivalent to the slope, but it's also equivalent to the stretch or the squish of the function. For instance, if the absolute value of a is between 0 and 1, then the function is stretched out more along the x-axis and gets more and more horizontal. But if the absolute value of a is greater than 1, then the function gets stretched out along the y-axis and becomes more and more vertical. Let's quickly run down on the other characteristics of these functions. The domain of these functions is all real numbers, negative infinity to positive infinity. There's no restriction on what I can put into x. Same for y. The values of y can be any real number from negative infinity to positive infinity. End behavior of these functions is determined by the sign of a. If a is positive, as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. The function goes from the bottom left-hand corner of the graph up to the top right corner. If a is negative, then as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches negative infinity. The graph goes from the top left-hand corner down to the bottom right-hand corner. Now, what about if a is equal to 0? Well, like all polynomials of which linear functions are a part, if the leading coefficient is 0, then it degrades the degree of the function down by 1. What I mean by this is that we no longer have a linear function, we now have a constant function. Y is equal to some constant number, which is equivalent to a horizontal line. Now, if a gets bigger and bigger and bigger and starts to approach infinity, then we get a vertical line. And this can no longer be represented by a function, but we can write it in the form x is equal to h, where h is the horizontal position of that vertical line on the x-axis. Finally, the parent function and all linear functions of the form y is equal to ax are something called odd functions. They have odd symmetry. This means that the function is symmetric across the origin. If I flip the function across the origin, then I get the other side of the function. The other way to put this in special math speak is that f of negative x is equal to negative f of x. If a function has this sort of relationship, then it is said to be an odd function. We'll talk about odd and even functions in later videos, but for now, linear functions of this form can always be said to be odd. In the next video, we're going to be checking out a problem using linear functions. But in the meantime, why don't you try it out yourself? What is the linear relationship between these 2 points? -4, -2, and 12, +2. What is the x-intercept of this function, and what is the y-intercept of this function? Try it out yourself, and I'll see you in the solution.